Hey there. In this video, we're going to talk about sinusoidal functions. These are functions that look like the sine function. So like sine and cosine, they look very similar. They both count as sinusoidal functions. And these are of incredible interest in the sciences because they describe oscillatory behavior and also the behavior of waves. So for instance, sound waves, what you're hearing right now is an oscillation of the air pressure coming at you, and it makes your eardrum vibrate like this. And if you think about that, that makes a sine wave. Also, if you think about a spring, the motion of an object on a spring, if you pull that object and let it go, it goes up and down, oscillates up and down, and if you track that over time, makes a sine wave. X-rays, gamma rays, radio waves, light behaves according to a wave. So these things are incredibly important in studying all kinds of behavior. So let's take a look. All right, so here we are in an application called Desmos. Desmos, written down here, as of the recording of this video, is freely available on the internet. So search for it, play around with it. It's great software. I was able to, in just a few minutes, set up this entire demonstration. And what I entered here was sine x, so we see a graph of sine. And I also have a transformation of the sine function using parameters a, b, c, and d. Now right now, a and b are equal to 1, and c and d are equal to 0. And so when you make those substitutions, you'll see that this is exactly the same as just sine x. So these two curves are right on top of each other. But what we're going to do is we're going to play with these parameters, a, b, c, and d, and see what effect they have on the shape of the curve. Okay, so let's start by tweaking this parameter a. If I increase a, what's going to happen? Well, we see that the height of the curve increases. It's a vertical stretch of the curve. If I make a number less than 1, I get a vertical squishing of the curve. I am stretching the curve vertically by a factor a. So when a is 2, the curve is twice as high as it was before. When a is 3, the curve is 3 times as high. And what this reflects is the amplitude of the wave. The amplitude is given by the distance between the middle line, which in this case is the x-axis, and the highest point. That is the amplitude. So right now we see the amplitude is 3. All right, I can also adjust a so that it's negative. What happens there? It flips upside down. It reflects the graph across the x-axis. Now the amplitude is still the distance from the middle line to the highest point. In this case, it's 2.5. Notice that that is not exactly equal to a. The amplitude is given by the absolute value of a. So let's return a to 1 and talk about the other parameters. All right, what about this parameter b? b is the parameter that's being multiplied by x inside of the sine function. What happens when I increase b? Oh, it does a horizontal squishing of the graph. If I make b less than 1, it stretches out the graph. So when b is large, I squish the graph. When b is a small number, I stretch out the graph. What's happening here is this is a horizontal scaling of the graph. Just like a was a vertical scaling of the graph, b is a horizontal scaling. And what happens is the graph is scaled by a factor 1 over b, the reciprocal of b. Now, the sine function has what's called a period. That's how long it takes for the graph to repeat itself. So if we start here and we go up the original sine curve, we come over here, we come back to where we start by the time we get to 2 pi. Once I get to 2 pi, the graph repeats. So every 2 pi units, it repeats. So 2 pi is the period of the sine function. Well, what happened when I adjusted the parameter b? Well, now I've got a new period. Now the period of this new function is pi over 2. By the time I get to pi over 2, the graph repeats itself. If I adjust b to just be 2, we see my period is now pi. What's happening here is that the period is always equal to 2 pi divided by the absolute value of b. What happens when we make b negative? If I make b negative, we see that the graph reflects across the y-axis, but it has the same properties. The period is still equal to 2 pi divided by the absolute value of b. So let's return b to the value 1 and take a look at these other parameters. All right, let's see what this parameter c does. Notice that c is the parameter that's being subtracted from the x inside of the trig function. Well, when I adjust c, I see that we have a shift of the graph. When c is positive, I shift the graph to the right. When c is negative, I shift the graph to the left. Now, it looks as though, the way I have it now, that the value of c is exactly equal to the amount of shift. But we should be careful of that, because you'll notice if I adjust b, it also adjusts how much the graph has been shifted. So the shift amount is actually a combination of b and c. The horizontal shift is always equal to c divided by b. Now I want to point out one more thing here. Let me return b to 1 so that we don't have to worry about the b. And I want to point out that when the c is 2, what you're going to see in here is a minus 2. It's a minus sign, but the c is positive. So when you see a minus a positive number, that's actually a shift to the right. And if c were negative, say negative 2, that's going to be a shift to the left. But what you'll see in here is a plus 2, because we're subtracting a negative number. So be sure to keep that in mind. When you actually see a minus, it's actually a shift to the right, and when you see a plus, it's a shift to the left. So let's return c to 0 and take a look at what d does. All right, well, d is the parameter that is on the outside of the trig function, and it's being added to it. So let's see what that does to the function when we adjust its value. Well, if I increase d, the graph goes up. If I decrease d, the graph goes down. And the extent to which it goes down is exactly the value of d. So if d is a negative 2, we've shifted the graph down 2 units. And if d is positive 3, we've shifted the graph up 3 units. So that's what d does to the graph. Now, I want to point out what will usually be the case is that you will see a combination of these things happening, and so you will have to be able to dissect all of this to figure out what these parameters actually were by looking at the picture, or else by looking at the parameters, figure out how to draw the picture. All right, so let's do a combination of things. Let's amplify the curve, so we'll make a equal to 2. Let's squish the curve a little bit by a factor of, say, 4. So we'll make b equal to 4. So now the period is 1/4 of what it was before. And let's shift the graph by some amount. Let's make c equal to negative pi over 2. And then let's do a vertical shift. Let's actually shift this graph downwards. So I'm actually going to subtract, well, let's subtract 1 from the graph. And so we can see that we've created a new sinusoidal curve. So you should, through practice, and you can play around with doing the same thing on Desmos to get good practice, you should be able to, by looking at these parameters, you should be able to determine what the graph will look like, but you should also be able to look at a graph and determine what the parameters were. Okay, so here's an example. This is a graph of a sinusoidal function, and we'd like to figure out what is its expression. Can we find the parameters a, b, c, and d so that we can write it in the form that we've been discussing? All right, well, first of all, let's see if we can find the middle line for this graph. Where is it centered? Well, it looks like it's centered right above, along this line. It goes an equal distance above and below the line going through y equals 2. Right? And how far above that line does it go? Well, it goes 1, 2, 3. So the amplitude is 3. So I can immediately write that down. A is 3. Now, what else can we see here? Well, we can check the period of this function. And how far do I have to go before the graph repeats itself? Well, over here, along here, over to here. How many units is that? That's 4 units. This graph has a period of 4. Now remember, the period is equal to 2 pi divided by the absolute value of b. So that is equal to 4. Solving this gives us the value of b. Right? So b, if I just use a little algebra here, we see that b equals plus or absolute value of b equals pi over 2. So b equals plus or minus pi over 2. We'll figure out which plus or minus it is in a little bit. All right. Now, what about c, the phase shift? Well, if I look at my original sine function, and I'll go ahead and plot it here. That's what the original sine function looks like. It doesn't look like it's been shifted to the left or right at all, because you see right where the original sine function crosses its midline over here at the origin, that's exactly where this function's crossing its midline. So it doesn't look like that's been shifted to the right or to the left. So it looks to me like c is equal to 0. And what about the vertical shift? Well, that looks like it's there, right? It looks like I took this middle line and it's been shifted up 1, 2 units. So the vertical shift, that's d, is equal to 2. So we've got everything except for the exact value of b. Now we know what happens when b is negative, right? When you make b negative, let me go ahead and do that with the original sine curve. You see what happened? It flips across the y-axis. Now that looks very different than what we have here. It looks like we don't have that. It looks like we have the same orientation, and so that's telling us that the b is actually going to be positive. So I'm actually going to exclude that negative answer and only include the positive one. b is positive pi over 2. And so we can write down our expression that way. Now, I'd just like to go through these steps and show you how that original sine curve gets transformed into the curve that we have here. All right, so let me go ahead and adjust a to make it equal to 3. So you can see when we do that, the amplitude increases to 3. I'm going to adjust b to be pi over 2. So let me insert pi over 2 over here. You can see what happened. The period has been shifted. Now, c we said should remain 0. And that makes sense. It doesn't look like I need to shift this thing to the right or to the left. All I've got to do is lift it up. How far up do I have to lift it? Well, 2 units. If I lift it up 2 units, I see I've found my curve. So that confirms what we found here. So that is the expression for our sinusoidal curve.